Welcome to the GCSE Combined Science Trilogy paper, the higher tier, Paper 1, 2023. Question 1. Wind power and solar power are both renewable energy resources used to generate electricity for the national grid. Which of the following is also a renewable energy source? Renewable means that the energy won't run out. It renews itself. It has no end date. Geothermal is the answer here, and that's because the heat from inside the Earth will not run out. It is replenished by radioactive decay inside the Earth, whereas natural gas and nuclear fuel are both things that are drilled and mined for, and one day will run out. There is one mark available. You can see on the mark scheme that the answer is geothermal, one mark available. Next question. The energy transferred by the national grid in 1 second was 36 gigajoules. Which of the following is the same as 36 gigajoules? Giga is a prefix. A prefix is something that alters the number in the same way that you would say 5 million or 5 billion. The million and the billion are both prefixes, but in science we use things like kilo, mega, giga. Giga means times 10 to the power of 9. So this is 36 gigajoules, or 36 times 10 to the power of 9 joules. Notice that the times 10 to the power 9 fits the space where giga previously was. 36 gigajoules. The giga is now removed and replaced with what it means. So the answer is 36 times 10 to the power of 9, which you can see in the mark scheme is correct. Figure 1 shows how the mean, or average, power output from solar and wind energy resources in the UK varied between 2014 and 2019. So on the x-axis, we can see we have the year, and we have a bar chart. We have separation between the data. This is discontinuous data. And we can see a pattern. These darker rectangles are gradually getting larger, but seem to plateau towards the end. They seem to have reached a peak. The grey boxes here also are exhibiting a pattern. They're going up, down, and then significantly up. And the height of them represents the average, the mean power output in, and we have another prefix, megawatts. Mega means times 10 to the power of 6, and here we have watts. Figure 2 shows how the power output from solar and wind energy resources varies in a typical year. So on the x-axis, we have the month going from January all the way through to December. And on the y-axis, again, we've got the power output in megawatts once more. We can see that there are two lines. The solid line is wind power, and the dotted line is solar power. So here is the wind power, and here is the solar power. Because the y-axes are both showing the same thing, the power output in megawatts, we can directly compare these numbers. So 3,000 here is the same as 3,000 over here. They are the same number. Explain the changes in power output from solar and wind energy resources between 2014 and 2019. So that takes us from the start all the way through to the end of this graph. And this shows a typical year. You should include an explanation of the change in power output during a typical year. Now this is a 6-mark question. Okay. I'm not going to compose an answer for this. What I'm going to do is I'm going to review the mark scheme. So this is a levelled question, and I've previously spoken about levelled questions, so I won't go into it in much detail here. We start at the bottom, and if there is no relevant content, we get 0 marks. To achieve level 1, which will get you 1 or 2 marks, you need to have points that are identified and stated simply, but relevance is not clear and there's no attempt at logical thinking. To get either 3 or 4 marks, that would be a level 2 answer, where you make relevant points, which include reasons and causes. These are identified and there are attempts at logical thinking. The resulting account is not fully clear. To get 5 or 6 marks and a level 3 response, you are making relevant points, which are reasons or causes, and these are identified, given in detail and logically linked to form a clear account. Given in detail means that you are quoting values from the graphs. So here are some of the things that you should include in essentially what is going to be an essay here. The information available in figure 1 allows you to identify that the wind power, which is the lighter grey and the dark grey being the solar power, it allows you to identify that the power output from wind has increased between this and this period of time. The pattern is that that is increased. And this is likely to be because more wind turbines were built during that time. Wind power comes from wind turbines. If we have more wind power, then it's logical to state that we have more wind turbines. You should also be identifying the fact that solar power is also increasing. We start off down here. You can read the value off the graph, and we end up in that position, but it's not increasing as much as wind. All of these values can be read off the graph and should be quoted. You might want to calculate the difference. So for example, this level over here compared with that level here. So you could quote the difference and read that off the graph. That difference would be 1,000 megawatts. For the wind power, again, you might want to quote the difference. It would be the difference between these values, and this difference would be 3,800 megawatts. And the increase in the solar power is likely because there are more solar panels being built. Now, recall that this is indicative content. You don't have to have put all of these. These are just points that are likely to be made from the evidence available. You might want to say that power output from wind and solar may have increased because of climate change, because in a warmer climate, what happens is that you get more dramatic weather. There are more sunny days, and so solar power increases, and there are more high winds, there are more storms. So that might also be a contribution to the increase in wind power, not just the number of wind turbines. There is a slightly unusual pattern that breaks the general pattern, and that is between these 2 years here, 2015 to 2016, where the wind power actually decreases, and you may wish to comment. Perhaps it's because 2016 was less windy than 2015. In figure 2, we can see very definite patterns here in wind power, where we have high winds in the winter months and also in autumn. And in solar, we have more solar output during the summer months than we do the winter. Some other observations you may want to make is that the level of wind is typically above the level of solar, apart from the middle of summer. And you may want to hazard a guess at some of the reasons for these patterns. So, for example, winter is a windier time of year than the summertime, and the summer is a sunnier time of year compared with winter. And that's why you get more power generated by wind in winter and more generated by solar in summer. The mark scheme makes it very clear that in order to be considered for level 3, your answer needs to describe the trends in both graphs. That is, describing how the data is changing across the graph. Not just identifying individual values and quoting them, but describing the changes. And they are looking for you to be suggesting reasons for those changes. Question 2. Body analysis scales use the electrical resistance of a person's legs to estimate the percentage of water in the person's body. Figure 3 shows body analysis scales. And here we have figure 3. A person's legs contain both solid tissue and water. That solid tissue, by the way, might be bone, muscle, ligaments, any solid part of the body. And remember that things like blood contain a lot of water. A student used resistors to model the solid tissue and water. The student connected a 20 ohm resistor in parallel with a resistor called R. Recall that when you have two components in parallel with each other, what we are doing is we are creating a junction before and after another component. These two resistors are in parallel with each other, whereas these two resistors are in series with each other. There are no additional junctions. Figure 4 shows the circuit diagram. So here we have our power supply in the form of a battery. We have a switch in the open position, an ammeter, and then we have a parallel section where there are junctions. We have the resistor named R, and we have a 20 ohm resistor. That's the one mentioned in the question. To determine the total resistance of both resistors, a voltmeter must be connected into the circuit. Complete figure 4 to show where the voltmeter should be connected. In order to calculate the total resistance for both resistors, you're going to need two values. Resistance is voltage divided by current. So you're going to need the current going into both resistors, and you're going to need the voltage across both resistors. So the voltmeter should be drawn connecting either side of the resistors. You can do it in this position. You can do it in that position, as long as the connections that you're making are on the left side and the right side of the resistors. Another acceptable answer would be putting the voltmeter across just one of the resistors, so across this one, because the voltage across these two would be identical. If I was to put a voltmeter here, it would have the same reading. So there are lots of ways to get that mark. The student calculated the total resistance of the two resistors. The student's answer was 26 ohms. Explain why the student's answer cannot be correct. Let's have a look back at the diagram. We have the two resistors in parallel with each other. If we only had the 20 ohm resistor, then current would be whatever value it is. As soon as we add a second option for that current to travel, it's a little bit like adding a second road that goes through a town. Immediately, the traffic is eased. So that means that the current can increase. this means that the resistance of the network is lower. So it doesn't matter what value resistor you put here, the resistance of this section should decrease, which is the opposite of what the student records. Notice that the 26 ohm is larger than the 20, when really we are expecting a value smaller than 20 ohms. The mark scheme is awarding 2 marks for your explanation. The statement that the total resistance must be less than 20 ohms, and explaining that this is because the total resistance of the resistors in parallel should be less than the value of the smallest resistor. For these 2 questions, we're expected to use an equation, and that equation is available on the datasheet. Write down the equation that links current, resistance, and potential difference. You can write out the word equation using these terms, or you can use the symbols. It's quicker to use the symbols. You can write it out with the multiplication sign or not. This is the more sophisticated version. It doesn't get you any more marks, but if you're thinking about doing A-level, you should be starting to think this way. (2.4) When the total resistance of the resistors was 7.5 ohms, the current in the circuit was 480 milliamps. Here's another prefix. Milli means times 10 to the minus 3. Calculate the potential difference across the 2 resistors. So we are given a resistance, we are given a current, and we're being asked to calculate a voltage. I would encourage you to annotate the question using the symbols that you recognize from being the equations, so that it is easier to pull out the information that you're going to need and see which equation to use. So we're being asked to calculate the potential difference. So the equation is going to be potential difference, or V, is equal to IR, or I times by R. And then we need to make sure that we're using the prefix correctly. The value for current is 480 milli. So you have to put in times 10 to the power of 3. Otherwise you get the wrong answer. Multiplied by the value for R, for resistance, 7.5. You put that into the calculator. And you should be getting the answer on the mark scheme, which is 3.6 volts. It's good practice to add your answer down here and double check that the unit is provided, because if the unit is not provided, then there is usually a mark available for providing the unit. Some people will convert the 480 milliamps into amps by doing it a different way. With milli, you expect the number to get smaller, in the same way that if you had 1,000 millimeters, then you would expect a smaller number of meters out of that. So we would expect it to get smaller, so we're going to divide. Milli is 1,000th, so we are dividing by 1,000, and that would give you 0.480. And you could put that number into the equation. That's a different way of doing it, but again, if you're considering continuing on with physics, you want to be doing things the more sophisticated way, I would recommend this technique. It also means that you're not having to think very carefully about how the number ought to change, And instead what you're doing is you're just replacing the prefix with what it means. This technique leads to fewer errors. The student investigated how the resistance of R affected the total resistance of the circuit. Table 1 shows the results. So it's looking like that resistor, R, is actually a variable resistor, and these are the values that the student has changed it to. Or it could be that they have simply replaced that component with other resistors with known values. And we can see here that these numbers are going up, the value of R is increasing, and the total resistance of the circuit in ohms, the pattern again as we go down the table, that total resistance is also increasing. Some of the results are plotted in figure 5. Some, I would anticipate that we're going to be asked to put in the missing values. Complete figure 5. You should label both axes, plot the 2 remaining values from table 1, and draw a line of best fit. Notice that there are 3 bullet points and there are 3 marks available. Okay. So at the moment we don't know what value is on the y-axis and which value is on the x-axis, but we can work it out. I'm going to pick one of the values where the x and the y have different numbers. So here we have a value of 5 on the x-axis and a value of 4 on the y. So we can see 5 and 4. The 5 is the resistance of R in ohms, and the total resistance is the 4 going on the y-axis. So let's put those in now. So we've done that first step. Plot the 2 remaining values from table 1. Okay, so we can see that this is plotted. The 10, that's also plotted. And then we've got a large gap, and we've got one more, which is the 25. So the 15 and the 20 still need to be plotted. These two. So resistance of R is 15, and the total resistance of the circuit is 8.6. So 15. Find 8. Here is 9. Notice that it's going from 8 up to 10, so the middle has to be 9. If we have a look, we can see that there are 1, 2, 3, 4, 5 intervals in between. 8 to 9 in 5 intervals should be in 0.2s. Let's check. 8.2, 8.4, 8.6, 8.8, 9. Yes, it's going up in 0.2s. So 15, here's the 15. We go up to the 8, 8.2, 8.4, 8.6. You need to be plotting these accurately. Next one, 20, and we have to plot 10. That's a lot easier, but no excuses for that being plotted incorrectly. Notice on the mark scheme that it says that the x-axis needs to be labelled as resistance of R in ohms, and to get that mark, you'd also need to label the y-axis as the total resistance in ohms. To get the second mark, both points need to be plotted correctly, and notice that they have to be plotted within half of one of the small squares. Otherwise, the mark is not given. We can see from the data that the line of best fit is not going to be straight. We can see that it is curved, so we need to draw it curved. I'm going to start at the origin, and that's because it makes sense to. We have 2 resistors in parallel with each other. One of them is R. If R had a resistance of 0, then that would mean that it's a short circuit. And what would happen here is that all of the current would flow through that section. None of it would flow through the other resistor, and therefore the resistance would be zero because it's just a section of wire. So it makes sense that if the value of R is zero, then the total resistance of the circuit is also zero. It makes sense that there would be a data point here if we looked for it. So I'm going to start at the origin, and I'm going to draw a curved line of best fit. Now, if there was a data point as an outlier, you would be expected to ignore it. And it specifies in the mark scheme to ignore outliers. If, for example, you had plotted this point incorrectly, you would be expected to ignore it as an outlier, like this. But if you plot it correctly, you should get a smooth, curved line of best fit. What resistance of R would give a total resistance of 4.4 ohms? You need to read this off your line of best fit. 4.4 ohms. You need to find that location on the y-axis because the y-axis shows the total resistance. We know that it goes up in 0.2s. We can double check that and go through that process again if necessary. 4.2, 4.4. And it's a good idea to label that, not for the examiner, but for yourself. Because when you come back and check your work, you can see that what you've read off the graph matches what's in the question. Use a ruler and a pencil to go to the line and then immediately downwards. And you're getting a value of, we've not had a look at the intervals on the x-axis, so let's do that now. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 intervals to get 5. That indicates that each one of these is 0.5. So 2 would be 1, 2, 3, 4, 5. So each one of these squares is 0.5. We are between the first and second, so that would be 5.5 and 6. 6 is over there. So I would record this as being between 5.5 and 6. 5.75 ohms. Notice on the mark scheme, they allow any answer, errors carried forward here, as long as it's within half a small square of what it is that you have drawn. The body analysis scales initially show a reading of 0 kilograms. When the student steps onto the scales, the reading is 64.8 kilograms. The student steps off the scales, then immediately steps back on. The scales now show a reading of 64.1. These two values should be the same. Complete the sentence. The difference between the two values given by the scales is due to A. It's not a 0 error because we can see that it did read 0 when there was nothing to measure. This is a random error. There is no apparent cause and there's no apparent way to correct for it. So this would be a random error. The height of the student is programmed into the scales. The scales place the student into a category, A, B, or C, based on height and mass. Figure 6 shows how the scales use the category and the total resistance of the legs to determine the body water percentage. So on the y-axis, we can see that this is a percentage of water. It goes from 0 up to 90, but we can see that if we continue the scale, that would be 100. On the x-axis, we've got the total resistance of the legs in kiloohms. Kilo is another prefix, and it is times 10 to the power of 3. It ranges from 0 up to 1200, but using this scale, you can see that that value is 5 squares above. And if we have a look here, we can see that 5 squares above would be that middle. Between 1000 and 1200 would be 1100, and therefore this distance here is worth 100. So this scale goes up to 1300. The total resistance of the student's legs is 600 kiloohms. Notice that the graph is already plotting in kiloohms, so we just need to pay attention to the 600. We do not need to correct for the prefix. A healthy body water percentage is between 45 and 65%. 45 would be here, and 65 would be here, within this range. The different measurements of the mass of the student mean that the student could be in either category A or category B. Evaluate if the student has a healthy body water percentage. 3 marks available. So we need to plot the 600 kiloohms onto our graph for either category A or category B. So you would get a pencil and a ruler and draw a vertical straight line from that position up to A and then across. Which gives 61%. For category B, you would continue your line up to B and then across, which would be 68%. And that value falls outside of this healthy range. So we need to evaluate if the student has a healthy body water percentage. You get 1 mark for identifying the category A value, 1 mark for stating the category B value, and a 3rd mark for stating, as it says in the mark scheme, that if they are category A, then the body water percentage is healthy, but if they're category B, they would be in the unhealthy body water percentage range. Question 3. Figure 7 shows how the national grid transfers energy from a power station, over here, to some street lamps, over here. Explain how transformer X increases the efficiency of the national grid. So in explain, you are usually stating some evidence and linking it to the science. So here we're going to state the function of a transformer and linking it to the science of efficiency. Okay. So the transformer next to the power station is receiving a current and a voltage from the power station. And if we multiply these values together, we have power. That power is going to be the same everywhere within the system. It will be the same at the streetlights and inside the transmission cables. That power is a value that remains the same all the way through. The reason for that is because power is energy per unit time, and energy is always conserved. Transformer changes the balance of current and voltage. If it is a step up transformer, then what happens is that the current and the voltage are changed so that the current goes down and the voltage increases. A step down transformer takes that small current and that large voltage and puts them back as they were. Or if you have just a normal current and voltage, it makes the current very, very large and the voltage very small. So when we think of the up and the down, we're thinking about how is the voltage changing. The voltage is going up, the voltage is going down. You are being asked about this transformer here, transformer X. This transformer is a step-up transformer. A step-up transformer. So you want to explain that a step-up transformer increases the voltage and decreases the current. You get 1 mark for each of those statements. The reason for this is because in the transmission cables, current causes heat. And the more current you have, the hotter the cables get. The hotter they are, the more energy is going to be lost to the environment. Think of an outdoor heater. We don't want to lose that energy, we want to keep it. So what we want is we want the current travelling through those transmission cables to be as small as possible. In order to do that and conserve the power, the voltage has to be increased. So we need that step-up transformer. And the reason for that is to reduce energy loss in the cables. And that's what the 3rd mark is for. You can express it in all sorts of different ways, and here are some examples in the mark scheme. 3.2. The potential difference across the primary coil in transformer Y. Recall that transformer Y is this one over here, receiving the very large voltage and reducing it back down to an acceptable level, ready to be used in the streetlights. So this transformer has to be a step down transformer. The potential difference across the primary coil in transformer Y, which is a step down, is 400,000 volts. Now, transformers have a primary and a secondary coil. The primary coil is the one that is coming in, and the secondary coil is the one that is coming out. Notice that I've done a larger number of turns on the primary and fewer turns on the secondary. The energy is going to be passed from the primary to the secondary, and in a step-down transformer, the number of turns decreases. It steps down. We're told that the primary coil has a voltage of 400,000 volts, and the potential difference across the secondary coil is only 11,000 volts. The current in the primary is 660 amps. We need to calculate the current in the secondary coil of transformer Y. We're going to use the fact that power remains constant in the system. So we're going to calculate the power for the primary, and that has to be the same power in the secondary. Okay, so the primary coil values are, the current is 660 amps, and the voltage in the primary is 400,000. The voltage is 400,000 11,000. Now, you could write an answer for that value, or you could carry on with the algebra and reduce the opportunity for making mistakes. If, for example, I wrote down this answer and I copied it down from the calculator incorrectly, I would then be using that number in further calculations. Introducing more steps means that you're introducing more opportunities for error. So for now, I'm going to keep that number as it is. In the secondary coil, I know that my power has to be equal to that value. What I don't know is the current. So that is also going to be equal to this value. So what I'll do is I'm going to rearrange this equation for the current. And then I'm going to substitute all the known values in. I know that the power has to be equal to whatever this value turns out to be. And then I'm dividing by the voltage in the secondary, which is 11,000. Now I put that into the calculator. It's one calculation, and the chances of making an error and then passing that on are eliminated. I'm just doing one calculation. The answer turns out to be 24,000. I'm going to write that down here. I can see that the unit is already provided amps because it's a current. (3.3) Why is the current in each street lamp less than the current in the secondary coil in transformer Y? So here is the current in the secondary coil. And what this question is telling us is that the current in each of the street lights is less than this value. Now, if our power supply and our components are connected in series, then we would expect the current to be the same in all of them, because the current flows from one to the next to the next. So we know that that cannot be the case for these street lights. The opposite of a series circuit is a parallel circuit. So this is the answer. Let's have a look at the wrong answers and discuss why they're wrong. Current is used up. That is a very common misconception. Current is never used up. The current that you have exiting the power supply is the same as coming back into the power supply. Some of the current is dissipated to the surroundings. Energy can be dissipated to the surroundings, but not current. Current flows through the wires only. The cables between Y and the street lamps have electrical resistance. That could be true, but that doesn't change the values. If that were true, that they have electrical resistance, then it would reduce this value as well. The only answer that makes sense is this one. (3.4) Figure 8 shows the top of a street lamp. Here we have figure 8. We have a light sensor, which is probably an LDR, a light-dependent resistor, and a lamp. The light sensor detects if it is day or night, if it is light or if it is dark. Figure 9 shows part of the circuit in the light sensor. So we have our battery, our power supply, a resistor with value R or name R, and here we have an LDR, a light-dependent resistor. Explain what happens to the potential difference across resistor R as the light intensity decreases. So the potential difference across resistor R, we're going to draw in this imaginary voltmeter so that we can picture what's going to happen. We want to know if the value at this voltmeter goes up or whether it goes down. What's happening in this circuit is that we have a battery, and that battery is sending out a current. The amount of current that goes out depends on the total resistance within the circuit. So let's put in a couple of imaginary figures. Let's say that the value of resistor R is 100 ohms and the value of the LDR is also 100 ohms. As the light intensity decreases, the resistance of LDRs go up. So this 100 becomes 200. The total resistance in the circuit has increased. That has the effect of reducing the current coming out of the battery. The voltage across R is dependent on the resistance, which is fixed, and the current going through it. If the current has decreased, then what will happen is that the voltage dropped across the resistor will also decrease. So there are several marks available. There are 3 marks, and you get marks for the 3 separate statements. For the resistance going up, the current going down, and therefore the potential difference across R is also going to go down. Those are the 3 statements, and that's what the 3 marks are for. (3.5) When the current in resistor R is 20 milliamps, and we've seen milli before, so I won't explain that again, the power transferred by resistor R, the power is 6.0 watts. Calculate the resistance of resistor R. Okay, so we have P and I, and we're being asked to calculate R. One of the equations on the physics equations sheet is that power is equal to I squared R, which we can rearrange for resistance and substitute in the values. Power is 6.0, and then the current, which needs to be squared, is 20 milli, so times 10 to the minus 3. And that gives us 15,000 ohms. You might choose to write that as 15 kilo ohms, because kilo means 1,000. There is another way to do this calculation, and that is by calculating the voltage first. So, for example, we could use this equation and then put that into this equation. So rearrange for voltage, gives you a value for voltage, whatever that number turns out to be. And then we can rearrange V equals IR for R, and we put this value in here, knowing that I is 20 milliamps. So you could do it that way, but it's more steps. This way is definitely better. The fewer steps there are, the less opportunities there are to make mistakes. Question 4. A scientist investigated a sample of a radioactive material to determine if it would be suitable for medical use. The method, results, and conclusions of the scientist will need to be checked by other scientists before the results of the investigation are published. What name is given to this checking process? That is peer review. A peer is somebody who is on the same level as yourself, and a review is like a check. So checked, reviewed by other scientists. A scientist has written this, it needs to be checked by other scientists. That's where the peer comes from, and the checking is the review. Peer review. 4.2. There is an increased risk of cancer if the scientist is irradiated by nuclear radiation. What property of nuclear radiation causes the increased risk of cancer? The fact that it is ionizing. The ability to create ions, which is when you have a nucleus and the electrons around the nucleus are ripped away because you have something like an alpha particle passing close by, and they are strongly attracted and they are ripped away from the atom. This changes the chemistry of the atom, and if you start changing the chemistry of established chemical reactions inside the body, then you can cause damage. That can kill the cell, it can mutate it and have it turn cancerous. That's the danger. 4.3. The activity of a radioactive source is the rate at which the nuclei of the source decay. What is the unit for the activity of a radioactive source? That would be the becquerel. Now, you don't need to write it like this. You could write the unit. It's the equivalent of writing out the word meter when you should really be writing M for meter. So 3 meters, 3 meter, 5 becquerel, 5 becquerels. Okay, just do it that way. The scientist placed a radiation detector near the sample and measured the count rate. Explain why the count rate is less than the activity of the sample. So what you're trying to explain here is that you have a lump of radioactive material and it's giving out radiation in all directions. You place a small detector connected to a counter over here, and only the radiation that is directed towards the counter and enters it is going to be counted. All of the rest is going in the wrong direction and is not going to be measured by this device. So that's what we have to be able to explain here. You get marks in the mark scheme for stating not all the radiation emitted by the sample is going to be detected. And this is because, and there are lots of different ways of explaining this, and the mark scheme has got a variety of techniques here, because the radiation spreads out. Some radiation is absorbed before reaching the detector. That's true, especially for alpha. So if the detector is a very long way away, then it could be that the air has actually blocked it before it gets to the detector. Or if the radiation is emitted deep inside the material, it might be absorbed before it even gets to the surface. This is the main point, however, that radiation is emitted from the source in all directions, and only some of that is directed towards the detector. .5. The scientist recorded the count rate from the sample with the radiation detector at different distances from the sample. So here we have table 2 showing those results. We've got the distance between the sample and the detector in centimetres. So here's our sample, here's our detector, and this distance here is measured there. And then we have the count rate. So what was it that the detector was able to detect when it was at those different distances? So it could have been a long way away, or it could have been very close. Okay, a very small distance here. So this is the smallest distance. And we notice that when the distance is very small, we get a larger count rate. Explain which type of radiation was emitted by the sample. So we can see that very, very close up, we get a very large count rate, which rapidly decreases to 0. Now, if this was gamma radiation, it would decrease rapidly but it would never decrease to 0. And that's because there is always going to be some radiation emitted in that direction. The 0 is the most significant number here. It tells us that after about 10 centimeters in the air, no radiation is making it through. And that tells us that it is alpha. Beta would behave a lot like gamma. Alpha is the only one that behaves like this. There is a cutoff. We need to explain which type of radiation was emitted by the sample. So we get a mark for stating that it is alpha radiation, and the second mark is for justifying that statement. In the mark scheme, there are several different ways of wording this, and these are all the ones that get the mark, because radiation is not detected beyond 5 centimeters, because alpha radiation cannot travel 10 centimeters in the air. You could explain it in the other way, that beta and gamma radiation would be detected because they travel that far. But basically, it's because alpha radiation cannot travel more than a few centimeters in air. 4.6. The scientist moved the detector closer to the sample and started a stopwatch. The scientist measured the count rate from the sample at different times. Table 3 shows the results. So here we have a situation where the sample and the detector are at a fixed distance from each other, and that value does not change. What changes is that there is a stopwatch, and we are timing how many decays are being detected by the detector in these many minutes. So we start the counter and we start the timer. At 0 time, so in the first minute, we are recording a count rate that's very high, and this count rate is per second. So we're getting that many per second within that first minute. At the 30-minute mark, we have an unknown value, and at the 60-minute mark, the count rate per second has gone down to 98. The scientist realized that 30 minutes is a whole number of half-lives. So what we could do is we could analyze this number and half it until we get to 98. Let's do that now. So 1,568, one half-life, it would have reduced to 784. After the next half-life, it would have reduced to 392. Halve it again, and it would have reduced to 196. Halve it again, and we get down to 98. So that is 1, 2, 3, 4 half-lives. So from here to here, it is 4 half-lives. In order to get to x, we're not going to 60, we're going to 30. Okay, so if 60 minutes is 4 half-lives, then that would be 15 minutes is equal to 1 half-life. So 30 is 2 15s, or 2 half-lives. So calculate the value of x in table 3. You would show how you find out this value. You could say, therefore, 60 minutes is 4 half-lives, and 30 minutes is 2 half-lives. And if you're going to go 2 half-lives, you're going to go starting at 1,568. 1 half-life would take you here, and that second half-life would take you there. So we're expecting 392 counts per second. You get 1 mark for identifying this or an equivalent statement. You get another mark for making this statement or something equivalent to it, and you get the third mark for the final answer. The scientist had a second sample of the radioactive material. The scientist made appropriate measurements, then calculated the half-life of each sample. Why was the half-life collected from the second sample slightly different from the half-life collected from the first sample? However, the statement that it was only slightly different indicates that it is within the acceptable error. And that's why the answer is the first box here, that radioactive decay is a random process. And a random process is going to give you slightly different values each time. The count rate from a radioactive sample is predictable. It is sort of within a slightly different range each time. So that's not an appropriate answer. It will change slightly. The samples were at different temperatures. Temperature does not affect decay rates. It affects the rate of chemical reactions, but we're talking about a nuclear process here, and temperature does not affect nuclear processes. The size of each sample was different. That would affect the count rate, but it would not affect the half-life. Question 5. Figure 10 shows a child's toy. A child pushes down on the toy to compress the spring. The spring then launches the toy into the air. So it would extend again, and the whole thing would be launched upwards. 5.1. A student measured the maximum height reached by the toy. The student placed a vertical metal rule near the toy. Here's our metal rule in a vertical position in both figures. And the student observed the height reached by the toy. The student repeated the experiment, observing from a different position. Figure 11 shows the toy at its maximum height and the two positions of the student. Observing the toy from position B instead of position A affected the measurement of the maximum height reached by the toy. Explain how. So it didn't affect the maximum height. We can see in the diagram that the maximum height is the same in both diagrams. It affected the measurement of the maximum height. So what we can see here is that the eye line to the bottom of the toy would give you a measurement up here, and the eye line in position B would give you a measurement down there, which are completely different measurements. This is a parallax error. Parallax being a measurement difference caused by the point of view of the observer. This is good practice. This is poor practice. So position B is the more accurate measurement. Okay, and you want to be explaining this and get your 2 marks. Okay, so in the mark scheme we can see that you get 1 mark for stating that the measurement will be more accurate in B, and this reduces the parallax error, and this is because the eye is level with the bottom of the toy, and therefore that is the more accurate measurement. You might want to annotate the diagrams as part of your answer. That would probably help you explain what it is that you're trying to demonstrate. 5.2. The greatest height reached by the toy was 64 centimeters. The gravitational potential energy of the toy at this height was 0.049 joules. Gravitational field strength is 9.8 newtons per kilogram. Calculate the mass of the toy. You can use the physics equations sheet to get the equation that you need. So we are given the height, We are given the gravitational potential energy at that height. We are given the gravitational field strength, and we're asked to calculate the mass. Now, when you annotate the question with the variables, you can see all of the parts of the gravitational potential energy equation as it appears on the datasheet. Rearrange for the mass and substitute. Here's our value for gravitational potential energy. There's our value for gravity. And here's our value for height. Now the problem here is that there's a prefix. Centi means times 10 to the power of negative 2. So let's put that in with our answer. 64 times 10 to the power of negative 2. And if you type this into your calculator, you get a value of 0.00781225 kilograms. Now that's a lot of significant figures, and this is deliberate in the question because you're told to give your answer to two significant figures. In fact, you're told this twice. So hint, hint, you're going to lose a mark if you don't do that. Okay, all of these are ignored. One significant figure, two significant figures. The next value is 1, so there's no rounding. We are going to write 0.0078. The unit is already there, so we don't need to include it. If the unit was missing, then we would need to include that unit to get the mark. 5.3. When the spring launches the toy into the air, the temperature of the air increases. Explain why the child's toy on its own is not a closed system. So we've got the toy, and as it launches into the air, it's going to be pushing past the air in order to gain height. Just like a parachutist who is coming down, this object is moving up through the air and is experiencing friction with the air, drag, air resistance, and that has the effect of heating up the air as it moves through. Now, a closed system refers to things that we are considering, things that we are thinking about, and everything else is outside the system, is outside our consideration. So we need to explain why the child's toy on its own is not a closed system when we include this sentence here. The temperature of the air increases. So what is not included with this here, this system, what's not included is the movement of that air and the friction. Okay, so we need to explain that if we're aware of the temperature increasing, then we need to include the air around the object in that system as well. So we can say that because the temperature of the air is increasing, then energy is being dissipated to the surroundings. Now, I don't want to go outside the box. I want to make sure that all my answer is going to be scanned in. So energy is being dissipated to the surroundings. Whereas if we had included everything that we're considering in the system, then there wouldn't be any energy loss to that system. So in a closed system, there is no energy loss. Okay, if we have a look at the mark scheme, that is explained in several different ways. You get the first mark for identifying that energy is being lost to the air, and the second mark for being able to link that to a closed system. Okay. Question 6. Figure 12 shows a device that uses a mug of hot coffee to turn a wheel. Okay. 6.1. The hot coffee, down here, so we can see that this is a glass mug. It's quite difficult in this diagram to see, but we've got a glass mug with a handle and we've got some coffee inside the mug. And then on top of here we have an air chamber, apparently, we have a piston, and pistons tend to have two parts, and this goes up and down, okay, and there's a gap in the middle, okay, and the end of that piston is connected to the wheel. Okay, the hot coffee increases the temperature of the air inside the chamber. Explain how the pressure in the chamber changes. In order to get all 3 marks, you want to explain how the pressure changes, in what way, whether it goes up or whether it goes down. That will probably get you 1 of the marks. And then you want to state and explain the physics of what is happening. So according to the mark scheme, in order to get the first mark, you need to identify that when things increase in temperature, the particles move faster. You could also state that a different way by saying that they have a higher kinetic energy. The second point to get the next mark is that the particles are going to collide with the wall of the container. You can either say that they're going to collide more frequently, or you could say that they're going to collide with more force. Both are true. If you have a container, and inside that container are particles with kinetic energy, if you increase the temperature of those particles, then you're going to be increasing the kinetic energy and therefore the speed of the particles. Because they're moving faster, they're going to cover more distance, and that means that they're going to collide with the container more often than they were previously, because they're just moving faster inside. They're covering the distance across the side of the container. They're covering that distance faster than they were before, so you're going to have more collisions per second. These collisions are also going to be with greater force because they're moving with a faster velocity. So when they do hit, they hit harder. Either of those points would get you the second mark, and because of this reason, pressure is going to increase. So we want to say that the kinetic energy of the particles increases. You could also say that the speed of the particle increases when the temperature goes up. We're going to get a greater force with collision colliding with the walls of the container, and we can link that to pressure because pressure is force per unit area. If we get a greater force across that area, we're going to get a greater pressure. Okay, 1 mark, 2 marks, 3 marks. 6.2. For the device to work, the air in the chamber must increase in temperature quickly. Explain why the bottom of the air chamber is made of metal rather than plastic. Okay, so metals conduct better than plastic. And that means that energy can move through them faster. In the mark scheme, we can see that they've said that metals have a higher thermal conductivity. That's just a fancy way of saying that they conduct heat better. Maybe we could have put heat in here. But words to that effect would have got you that mark. Allow metals are good or better thermal conductors. Notice that thermal is in brackets. That means that word is not required. So I didn't need to make that change, but I feel better having that word in. This allows a greater rate of thermal transfer, or energy moves through the metal faster than the plastic. Energy is transferred more quickly, which is what I've said, words to that effect. And that gets you both marks. 6.3, the mass of the air in the chamber is constant. So here we have our air chamber, and the mass that's inside that is held at a constant value. What property of the air, so this is a state question, we're just going to give a single answer, maybe one word. What or which property of air allows a small change in internal energy to cause a large temperature change to the air in the chamber? So we want a small change to the internal energy to cause a large temperature change to the air in the chamber. Okay, we're linking energy, temperature change. There is an equation that describes the way that energy is related to temperature change. We can see that the mass is being held constant, so it can't be to do with the mass. The only thing left is the specific heat capacity. Now, the specific heat capacity is measured in joules per kilogram per degree C. It's the amount of energy that it takes to heat a mass by 1 degree. So if this value is very, very large, then it's going to take a lot of energy to get a small temperature change. We want a little bit of energy creating a large temperature change, so the specific heat capacity is low or small. If it's small, then it takes a small amount of energy to get a big temperature change. And that's the answer. 6.4. The changes in pressure in the air chamber cause the wheel to turn. So here's our air chamber. We've got a rotating wheel here, and it's done so via the piston. The changes in pressure in the air chamber cause the wheel to turn. Suggest one way, so there are multiple options for getting this correct answer. Suggest one way to increase the speed at which the wheel turns. Okay, so we're dealing with a mechanical device here. Any mechanical device is going to be susceptible to friction. So anything that can lower friction, whether that's using oil for lubrication, that would probably be an acceptable answer. Other things that you can get are, we are trying to cause a change in pressure that results in the wheel turning. We've been having a look at the past questions where we are looking at the pressure change, and we can see the pressure is going to be affected by the kinetic energy of the particles caused by the temperature increase. So another way that we could do this would be to increase the temperature of the coffee. And let's look at the mark scheme. Yep, we've got the first two. Decrease the temperature of the surroundings. That would cause a greater difference between the external system and the closed system. And any time that you have that, you're going to have a greater pressure differential. So that would affect the operation of the piston. I get the distinct impression that that option is very rarely written, or was very rarely written in that year. And sometimes what happens is that when a student writes an answer and it's a perfectly reasonable response, but it's just incredibly unusual that they would have picked that one, sometimes that answer is added onto the mark scheme afterwards, and this feels like one of those. One student, or maybe two out of all the thousands that are sitting the paper, have made that point, and it's technically correct. So they've added it onto the mark scheme because people have said it, and yeah, it turns out that it was right. 6.5. The temperature of the coffee decreases as the device is used. And then we're given a bunch of data and asked to calculate the final temperature of the coffee. Okay, I noticed that this is a 6-mark question, and it's a calculation question. So we need to approach this logically, one step at a time, and we need to be very careful about our algebra here. If you run out of space, use the additional sheets. Plan what you're going to do very carefully. So I'm going to label all the information that we have. We're being asked to calculate the final temperature, TF. We're given the initial temperature. Here's all of our data. The internal energy of the coffee, the energy decreased by that amount. So we could put that in as a negative number potentially. The density of coffee, that's unusual. Density and volume. Okay, those two values are connected with this equation, which is how we can access the mass, presumably. Specific heat capacity of coffee, that's our value for there. So we've got everything that we need for this equation. We're not given the mass on its own, we're given the density and the volume, but we can calculate the mass. So you may want to do this algebraically, or you may want to do it in stages and calculate the values. I'll show you both techniques. So we know that we're going to need the mass, so let's calculate it. Density is mass per unit volume, and therefore mass is going to be the density times by the volume. So the density, 1.1 times 10 to the power 3, multiplied by the volume, 1.9 times 10 to the power of minus 4. The mass has a value of 0.209 kilograms. Okay, so we have our mass. We need to find the final temperature of the coffee. So there's our equation. Let's rearrange for change in temperature. Now, the change in temperature is going to be the final value minus the initial value. Okay, but putting that in right now might make things a little bit more complicated. So let's just do it like this. We need to rearrange for the change in temperature. So the change in temperature is going to be this. The energy, the value of the decrease is 15 kilo. Kilo is times 10 to the power 3, or you may prefer to write 1,000. I prefer to write times 10 to the power 3. Mass, we've just calculated it. You need to use the number that's on your calculator, not a rounded value. And the specific heat capacity, which is 4,200. The change in temperature, that gives you a value of 17 points, about 1 degrees. Okay, if you know the initial temperature and it's cooling down to reach a final temperature, this is the change. So we don't want the change anymore. We want final temperature. We know that it's getting cooler. So you want to take the starting value and take away how much it cooled down by. And that gives you the final temperature of 59 approximately degrees. Final temperature coffee, 59 degrees. Okay, let me show you how to do an algebraic version, a purely algebraic version. So we know that this is true, and we know that this is true, but this is really final minus initial. So we could just go straight to the final temperature of the coffee, but we'd have to do a bit of algebra in order to get there. So instead of mass, I'm going to write what mass is equal to. And we know from this equation that mass is equal to density times by volume. So instead of mass, I'm going to write density times by volume. There we have that. Let's expand the change in temperature. Final minus initial. And then I suppose we could rearrange for final straight away. Let's go through a couple of steps first, just so that you can see what I'm doing. So and there we have that. So when we put all of the numbers in, we should get our answer there. So you could do it that way. Either works. And that is the end of the questions.